Here we go. Today we're talking about two smaller topics within the rotational unit. We're going to be talking about rotational kinetic energy, and then we're going to talk about rotational or angular momentum and angular impulse. Let's start with rotational kinetic energy. Because here's the deal. Pretty much throughout the whole year, we've been talking about kinetic energy like this, right? Kinetic energy is equal to 1/2 mv squared. I'm here to tell you that there's actually a secret second type of of kinetic energy that we haven't talked about yet. Because here's the truth. This type of kinetic energy is actually, it's called translational kinetic energy. It is the kinetic energy inherent in an object that is changing positions. It's translating, right? It's moving from one spot to another. But there's this other type of kinetic energy for an object that is spinning. We call it rotational kinetic energy. Right? Because if an object were spinning, not necessarily moving locations, but just spinning, it is still technically moving, right? So it therefore must have kinetic energy. That's what this is all about. So to produce our rotational kinetic energy equation, all we got to do is we're going to essentially translate these variables into rotational versions of themselves. Like, for instance, we know that the rotational version of velocity is just going to be angular velocity, right? Omega. So we know there's going to be an omega squared there. We're also going to swap out, rather than mass, we're going to swap that out for rotational inertia. That's kind of our rotational version of mass. I don't want to say that is that because mass doesn't really rotate. It's not really linear, but it's kind of our rotational version of mass. So yeah, there you go. That's it. That is our new type of kinetic energy. We now have translational kinetic energy and we have rotational kinetic energy. There isn't much more to add to it than that. We just have this new type of energy that we have to take into consideration when looking at different problems. Speaking of which, here is a practice problem to kind of test this out. So I have two identical ramps here. On the left, at the top of our ramp, we have a box. On the right, at the top of our ramp, we have a sphere. Both the box and sphere have the same mass of 2 kilograms. Both ramps have the same height of 3.5 meters. And we've been told that the sphere has a radius of 0.5 meters, and the rotational inertia equation for a sphere is 2/5 mr squared. So what I want to do is I want to compare their velocities at the bottom of the ramp. How am I going to do that? I'm going to use energy. It's going to be the easiest way for me to answer this question. So at the top of our ramp over here on the left, what type of energy does our box have? It's going to have potential energy, gravitational potential energy. What kind of energy is it going to have at the bottom of the ramp? Kinetic energy. But now we got to be more specific. What type of kinetic energy? Well, it's not rotating, right? So it's just going to be translational kinetic energy. It is moving from one spot to another. Meanwhile, over on our ramp here on the right, we, again, start with a bunch of gravitational potential energy. And at the bottom, we have a sphere. So it's going to be spinning at the bottom. So we're going to have rotational. But we're also going to have translational kinetic energy. We're going to have both types of kinetic energy. It is both spinning, it is rotating, and it is changing position. Therefore, it has both types of kinetic energy. All right, let's use that and jump to the next page. Here, I'm going to actually solve for those velocities. So, for the box, we start with a bunch of gravitational potential. We end with a bunch of translational kinetic. So mgh equals 1/2 mv squared. We've done this a million times this year. V equals the square root of 2gh. Plug that into my calculator. Comes out to something like 8. Let me double check the exact numbers there. Yeah, 8.28 is our velocity at the bottom. Okay, cool. That was easy. Now the slightly more difficult side of this is the sphere. Starts with a bunch of potential energy, converts to translational and rotational kinetic energy. All right, so let's swap out our equations here. 1/2 mv squared plus 1/2 I omega squared. All right, well, in order to figure this out, I need to solve for the linear velocity of the sphere, right? So I'm going to focus in over here on this rotational kinetic energy, and I'm going to swap a couple things out. I'm going to massage this so that we can actually solve for linear velocity. How am I going to do that? Well, I'm going to start by swapping out the rotational inertia equation, because we know what that is for a sphere. It's 2/5 mr squared. Then we have this omega here we got to get rid of. We can't have omega. We don't know our angular velocity at the bottom of the ramp. We got to get rid of it. In fact, I want to swap it out for linear velocity. How do we do that? Well, we have our translation equation. We know that linear velocity is equal to r times omega. Well, that means omega is equal to v over r. So I'm going to plug that in here. Don't forget that gets squared. Now things are actually going to kind of even out in a cool way here. So we have this squared attached to v and r over here on the right. Because this is r squared and that is r squared, those are going to cancel out. Also notice that across the whole thing, we have an m, right? So those are going to cancel out as well. Let's see what we're left with. GH equals 1/2 v squared plus 1/2 times 2/5 is 1/5. Also v squared. Interesting. So we add those two together. It comes out to 7/10 v squared equals GH. Solve for v, it comes out to be 10/7, square root of 10/7 times GH. Plug that into your calculator, you get 7 meters per second. There's your answer. So the sphere is actually going to be moving slower than the box. Why? Because it has rotational kinetic energy. The box only has to convert gravitational potential to translational kinetic. But the sphere has to convert to two different types of energy. It has to share that energy between the two. Therefore, it's going to have to be moving slower at the bottom. Okay, next up we have our shape race. I have 4 shapes here that I'm going to put at the top of this ramp that I've drawn. I have a hoop, a sphere, a box, and a disc. Okay? I've provided the rotational inertia equations for all of the various rotating objects. The question is, in what order are these going to hit the bottom of the ramp? I should mention, they all have the same mass, they all have the same radius, just to make things easy for us. We're going to order this race. We're going to see who gets first, second, third, and fourth. Well, in fact, the box I know is going to get first. Why? Because it's not rotating. We just saw in the last question that because the sphere had rotational kinetic energy, it must have a smaller translational kinetic energy or a smaller linear velocity. So everything that's rotating is going to be slower than the box. And that also kind of helps us point us in the right direction of the rest of this ranking. It's all going to come down to their rotational inertia. Because they all have the same mr squared, it's actually going to come down to just the coefficient that sits in front of that mr squared for their rotational inertia. Because the lower the rotational inertia, that means the more potential energy is going to get converted to translational kinetic. The lower rotational inertia, the higher the linear velocity. So I'm just going to order them in order of lowest to highest rotational inertia. So the rest of this race is going to be sphere in second, disc in third, and hoop in last. Which kind of makes sense because the higher rotational inertia hoop is going to be harder to get moving down the ramp, right? That's what rotational inertia is. It's our resistance to changes in rotational motion. It is going to be slower to accelerate down the ramp. Therefore, it's going to be last. All right, cool. Moving on to angular momentum. Again, we are going to take our linear versions of these and just translate them into rotational versions. Let's look over here on the left with linear momentum. We all know that linear momentum is equal to mass times velocity. So angular momentum, represented by a capital letter L, is going to be equal to rotational inertia, because that's kind of our analogy for mass in a rotational world, times angular velocity. Easy as that. What's nice about angular momentum is that it follows the same rules as linear momentum in that angular momentum is conserved unless there is an outside force acting on the system. Angular momentum is conserved unless there is an outside force acting on the system. There's a pretty good example of this that you'll see in most physics classes. Here on the left, I have a drawing of a student sitting in a chair that can freely rotate around its around the base it's on. No friction, no anything, it just can easily rotate. If we were to start this student spinning, they're holding some masses and they're holding them close to their chest to start. We start the student spinning and then the student reaches their arms out, they push the mass out as they hold their arms as straight as possible. What's going to happen to the rotation, the motion of this student? They're actually going to slow down. They're going to slow down. Why? Because angular momentum is being conserved. So looking at my equation up here, we're going to say that the initial angular momentum equals the final angular momentum. So check this out. We start the student spinning. They have a certain amount of rotational inertia and a certain amount of angular velocity. Then they push their arms out. They increase their rotational inertia. So in order for their initial angular velocity to be equal to their final angular velocity, initial angular momentum to be equal to their final angular momentum, the angular velocity is going to have to decrease. So as the rotational inertia increases, velocity decreases. Therefore, the student, when they're spinning, when they push those masses out, they slow down because angular momentum is being conserved. Okay, going back here, we now need to talk about angular impulse. We know that impulse is the change in momentum, and that is equal to force times time, as written up here. So again, we're just going to take that and come up with the rotational analogy. So in this case, the change in angular momentum is equal to torque times time. That's it. That's angular impulse there. Torque times time. Keep in mind that when you're solving for this torque, that is technically the average torque over the course of that time. All right, that's a little detail. Important to keep in mind though. Okay. Let's do a quick example problem. All right, I know there's a lot on this board. I'm going to use this little red dot to focus your attention. So here I have got two discs. Initially, both are at rest, but we know the mass of disc A is 9 kilograms, the mass of disc B is 6 kilograms. Both have a radius of 0.6, okay? Over here, we're told a little bit of information about the motion of disc A. It starts from rest, speeds up to 7.2 radians per second over the course of 2 seconds. All right? And then all the way over here, I've written our questions we're trying to answer. Part A, find the final angular momentum of mass A. Part B, find the torque required to speed up mass A to that angular momentum. And part C, mass B, the one up here, is going to be dropped on mass A. They're going to hit and stick together. We have to figure out what is their final velocity. And by the way, I've provided the rotational inertia for a disk. All right, let's go about solving this one. For part A, we have to find the angular momentum of disk A. Shouldn't be too hard. We know that angular momentum is rotational inertia times angular velocity. So we have the rotational inertia of a disk is 1/2 mr squared times omega. Now it's just plug and chug. We know the mass is 9. It's 9. The radius is 0.6. We square that times its angular velocity of 7.2. This comes out to an angular momentum of about 11.6. 11.6, ooh, forgot to mention units for angular momentum. That's going to be kilogram meters squared per second. Okay, that is our angular momentum after the object speeds up. Over on the right here, I got to solve for the torque acting on it. So what is that going to look like? Well, the final momentum minus the initial momentum equals torque times time. We know the final momentum is 11.6, the initial momentum is 0, torque is what we're solving for, time is 2, so torque is going to be equal to whatever 11.6 divided by 2 is. Of course, it's 5.8-ish, about 5.8. Okay, those two aren't too difficult. This is the difficult one, part C. So object B falls, hits object A, they stick together and start spinning together. Here I'm going to use this big, long-winded conservation of angular momentum equation. It's basically the same as what we did for conservation of linear momentum, just with the angular versions of them swapped out. So it's the initial momentum of object A plus the initial momentum of object B is going to equal the initial momentum of object B, or the final momentum of object B, plus the final momentum of object A. Okay, so let's do this. We know the initial momentum of object A is going to be 11.6. The initial momentum of object B is 0 because it is not spinning, so it is going to have it has no angular momentum, right? On the other side, we're actually going to have to add up the angular velocities, or sorry, rotational inertia of objects A and B, because they hit and stick together, right? So they essentially become one single object, okay? How are we going to do that? Well, it's going to be pretty simple. All we have to do, because they have the same radii, we're just going to add their masses together times the radius squared times omega f, and that all equals 11.6. I can now plug in some numbers here. So I got 1/2 of 9 plus 6 times their radius is 0.6 squared times omega f. Solve for omega f. It comes out to, I should probably solve this in my calculator real quick. We got 0.5 times 15 times 0.6 squared. Comes out to about 4.3 radians per second. All right, there you go. Those are our notes for rotational kinetic energy and angular momentum. Hope they were helpful. See you later.